This is a question from the thermodynamics topic looking at enthalpy, entropy and Gibbs free energy. Runs all the way to part D and it's worth 12 marks. So I'm going to recommend you pause on each section, try it and then review your answers. Here's part A, part B, part C and finally part D. And now we can start to review the answers. So we have got the equation provided. We want to know, using Le Chatelier's principle, the impact on equilibrium yield of hydrogen if we increase the overall pressure. Now I'm going to start off by looking at how many moles are on each side of the equation. And you can see there are 2 on the left and 4 on the right. Now I'm going to go to the explanation first and then put the effect in last, because obviously you're building up to your effect. Increasing pressure will favour a reaction that leads to a reduction in the number of moles. That means it's going to shift it to the left. And the reason for that is that it will be opposing the increase in pressure. Now that means if it's shifting to the left, our yield of hydrogen has decreased. Moving on, why would the equilibrium yield be unchanged if a catalyst is used in the reaction? A fairly straightforward and very common question. The catalyst speeds up the forward and backward reactions. Now it's lowering the activation energy of each by an equal amount. So we need to go a little bit further for the second mark. It does this by equal amounts. The rates are increased equally. Moving on, we have a calculation here. You've been given enthalpy of formation and entropy data, and in this case we want to know the enthalpy change for the reaction that we were dealing with. Now, I've put the equation here so that you can have a quick review if you haven't done it so far. And I'm going to build my Hess cycle. Now I've been given enthalpy of formation data, so let's put the elements down at the bottom, and I've got my enthalpy of formation of methane, and I've got my enthalpy of formation of water, so I can add those together and I get negative 317. I've also been given my enthalpy of formation of carbon monoxide and hydrogen. Hydrogen is 0 by definition, but it does mean that we've now got the data for the other 2 sides of the cycle. We only need the one that we're calculating. So I'm going to build up my 2 routes. I've identified those as the blue route and the green route, and I'm going to substitute those figures in to an expression that we can see here. I can then rearrange this to make x the subject, and that allows me to calculate that x is 206 kilojoules per mole. It's endothermic, it's a positive value for the forward reaction of the reversible reaction given. We're then going to move on. I've given you the data once again. We want to know the temperature at which this reaction becomes feasible. So first of all, we need to work out our delta S. That's the sum of the entropy of products, take away the sum of the entropy of reactants. I put the figures in. You can see I've multiplied the H2 by 3 because there are 3 moles in the equation. And I subtract my entropies of the reactants. No multiples because there's only 1 mole of each in the equation. This allows me to work out that delta S is 216 joules per Kelvin per mole, and I've now got 2 of the 5 marks. Third mark is for writing out my expression for delta G, which is delta H take T delta S. Now at delta G equals 0, we can be confident that delta H is equal to T delta S. So that means we can rearrange to make temperature the subject. Now I'm going to put my delta H value in that I calculated in part C. That's 206. And I'm going to divide by my entropy, my delta S value, 216. But I'm not going to stop there. My enthalpy is in kilojoules per mole. Delta G is in kilojoules per mole. But the entropy is in joules per Kelvin per mole. So I need to divide that 216 by 1000. When I do that, I get 954k. I've got my 4th mark, but we need to read this question very carefully because the answer needs to be in Celsius. So we're going to subtract 273, taking us to our value, 681 degrees C.